Nope. What do we want to do? There we go. Hi everyone, I'm Mark from Boondock Technologies, and in this live stream I'm going to show you how to build a inverted delta antenna, which is great for quick deploy HF operations. I did the 3D printing and I'll share the files with you so that it'll fit on a 1/2-inch rod that you can drive into the ground. And of particular interest to me today is the Balun that I made for it. It's a 4-to-1 guanella, and I'm going to show you how to do that. There's a lot going on in the world today, and people are scared of what can happen, and there's a lot of anxiety. One of the best cures for anxiety is action. So if you're worried about how you stay in contact with your friends in an emergency or anything of that sort, let's start with the Balun. You can get the antennas off eBay, and you can do a little 3D print. You'll have something you can pack. It'll fit right into your backpack, your radio backpack, and let you communicate with some amount of directionality. I'm not going to finish today. I've got an appointment coming up in a little over an hour, so I'm going to do what I can, and this will all get edited down into something a little more palatable. Field days next weekend, so hope you get out there and do stuff. All right. The inverted delta, or any loop antenna, requires a balanced input. That's not such a good thing because most radios these days have coaxial, which is an unbalanced output. We need something to bridge the gap, and we need to understand how that works. So I'm going to talk a little bit about theory because that's my jam, and I'm going to try to keep it at a level that is hopefully approachable. And once we have that figured out, we'll go from there. Oh, and I see I need to do a little bit of this. Let's see if I can get over even more. All right. Coming out of most radios these days is this thing called a B&C jack. And the B&C jack has these two little nubbin things on it, and depending on what the jack is, you might have a mount, or it might just be built right into the top. You could also get an SMA. It doesn't really matter. What it is a round shield and a center conductor, and that center conductor is where the radio energy exits the radio. Typically we'll add a piece of coax with another B&C connector that screws on a little bayonet, and we try to do what we can to keep all of that stuff inside a cable. And the cable is, probably could be doing some color here, but that's okay. But the cable is a piece of metal on the inside, just a solid piece of copper, followed by some copper braid all around the outside, called the jacket. And the idea is that when this signal travels down this center conductor, get it out of the way a little bit, that any radio energy will actually live in the dielectric material surrounding the center conductor. The center conductor isn't where the energy is. The energy, the changing electromagnetic fields, exist between that center conductor and the external shield. Or if I draw this a little bit bigger, right, we've got a center conductor and we've got that external shield. All of the energy, the polarization is happening in the area around the center conductor, between the center conductor and the shield. Now, that's all well and good, but what happens when you get to the end of the cable? Well, when you get to the end of the cable and you try to just throw an antenna on there, the energy starts to escape and radiate outwards. Okay, well, that's all well and good. But what happens if it reflects on something? Does the energy go back? And the answer is it does, but it doesn't go back inside the cable. What it does is it'll start traveling outside the cable. And we don't want that. So what we'll do is add this thing called a choke. And a choke is a magnetically permeable material. Usually we use iron and nickel alloys and other such things. And the energy will hit this thing and it'll get absorbed into it, and it just turns it into heat and it goes away. Oh, my art skills need some work there, Hughes. I'm going to have to work on that. All right, now let's take a look at an antenna. The antenna that we're building is an inverted delta antenna, and what we ideally want is that we drive each end of this antenna with an equal and opposite signal. If you're familiar with voltage versus time graphs, you know, like you might see on an oscilloscope, we'd have two equal in amplitude, 180 degrees out of phase signals feeding each of these antennas. But remember, I said our feed line the energy is traveling around the center conductor till it comes out. So which one do you hook it up to? Well, you can't. You need this thing in the middle called a balun, which connects the balanced output to the unbalanced input. And how the heck do we accomplish that? Let's find out together. It's physics. Love physics. All right. Surrounding every wire is, I can't think of a simple way to put it. In physics, we call it permeability and permeability. Let's call it this. Surrounding every wire is a field, and that field can store energy and it can release energy. What's really happening is that we're polarizing parts of it, and we can use that to push electrons around atoms. So if you have a signal traveling down this wire in this direction, it's going to manipulate the electric field around that wire. If we then put a second wire around there, this changing electric field is going to push on electrons and create a second one back the other way. So the longer this signal travels down, the bigger this return can be. And it grows, so as this signal goes down, this return is going to get bigger and bigger and bigger. It's a little bit out of scale. It's not really going to be bigger than this, but I needed to show that it was, just so you can kind of get an idea of what we're doing. If we can put our signal down one wire and then have it come back on both, we can turn our unbalanced to a balanced output. And the way that we do that is with these magnetic cores. It turns out that magnetic fields in air are pretty weak. Nothing is going to beat a magnetic field in a metal, and we'll talk about that in a little bit more in a minute too. But typically what we want to do is take a magnetic loop, set it near an iron core of some sort, run a wire down one side, run a wire down the other. Well, I just screwed up my drawing. Let me try that one more time. Sorry about that. It's going to come out in editing. So typically what we want to do is take 2 loops of wire, wrap them around an iron core, and when we induce an electromagnetic field, or when we run a changing electric pulse, oh, I don't want to overcomplicate this, and that's making me stumble. But when we run a signal through the first wire, it's going to create a changing electromagnetic field in this core, and then that core is going to create a changing electric field in this wire. So an unbalanced input will become a balanced output. Hopefully that kind of works for you. I put in a positive going signal here. I get a negative one out here. I put a negative one in here. I'm going to get a positive one out here. That's the way it works. So now I've got some cool animations that I spent way too much time making that I'd like to show you how they work, because it's fun stuff. All right. Surrounding all atoms are electrons, and the direction that those electrons spin is what gives us the electric field. And if they all spin in one direction, you get a strong field. If they're all out of order, you get no field. And you know, if you've got a little more than the other, you get a field. It's just not as strong. So we tend to call that spin. They're spin up, they're spin down. It's all sorts of this funny stuff. But if you broke these atoms into a grid, and you know, I'm going to start off with these things somewhat randomly assigned. The electrons are spinning all sorts of different ways, either spinning up or spinning down into the atom. Well, if you had an infinite grid of this stuff, and you applied an external electric field. So right now we're kind of looking sideways at it. So, you know, I'm going to apply a field. You can get these things to change. You can get these things to flip. And the thing that impacts any given atom, in this case, the center square one here is the only one I'm looking at, is what's going on with the nearest neighbors, what's going on with the external field, and what's going on with just a little bit of randomness that always exists in nature. We typically refer to that as the temperature T. So if this guy is going to flip or if he's going to stay in the same direction, it depends on what's happening nearby, what's happening, the strength of the electric field, and what's happening, because there's always just a little bit of randomness that we call temperature. With that, I've got some ridiculously cool animations I made to share with you. All right. And for those of you who are joining me, this is a live stream. I am making a Balun, but you know me, I can't shut up about physics long enough to do it. So this is the Balun that we're making. Right now I'm going through the theory a little bit, and then at the end this will all get cut down and we'll talk about it. We need cam 8. And I think I can go away for a minute. All right, we were talking about those little fields, those, you know, what's happening at each individual site as you go around. And there's this thing called an icing model. So if you have something, be it magnetic domains or crystals or whatever, Over time, it goes from random to ordered. You start getting this corseting effect that's happening. You go from this highly disordered system to a more ordered one. And if you've ever looked closely at like grain boundaries in metals, or this happens in crystals, it happens in lots of different things. But we have this thing called the icing model that develops it. Now, if I go back to the down cam for a second, what I'm about to do is take this field and flip it. So we're going to see the field go one way and then the other, and then one way and then the other. And it will be fun, maybe. I don't know. I geek out on this stuff. All right. A fast changing electric field. We're going back and forth. We're never fully saturating anything. Here it is with a little bit of a graph. You can see with every little bit of energy that we put in, we're kind of in this constant change, and that's a good thing, because the constant change means we're putting energy in and we're getting energy back out. We're putting energy in and we're getting energy back out. We're not losing much. But let's watch what happens if we change the frequency too slowly. And let's see if this is the right one. So here we're changing it very slowly. And you'll notice that, we're still putting energy in. And we're not seeing really anything change. We're not seeing flips. So the energy that we're putting in is wasting. It's going towards heating the core. I'll play that again. And the reason that this is important is for what we're about to do to work. We've got to be flipping these things to put energy into the core. We've got to flip it fast enough that we can still keep getting energy back out, because at some point you just saturate and you're putting more energy in and nothing's happening. So let me show you just of a simple quench. This would be, magnetizing something, and you get all these domains. Spin up is, white, spin down is black. Let me show you fast again. Okay, we're constantly changing, and we're constantly seeing change. Versus we do this thing too slow. We're still changing, but we're not seeing change. We've saturated. We don't want it. Saturation's bad. Oh, how do I... There we go. All right, so that's kind of a primer on this stuff. So what we're going to do, don't worry, I'm about to build. I talk a lot, but I eventually get it done. So what we're about to do, oh, Andy Cowley, Boondock Echo. Yes, I heard Boondock Echo. You found me. You will be my one viewer on this. I didn't announce this at all. All right, so what we're going to do is create a sorry, I can't talk and do both at once. What we're going to do is create a Balun, and this was created by Guanella. We're going to take the unbalanced side, I believe we cross these. Andy, thank you for joining me, Andy, brother. Appreciate you. All right, so my signal is going to come in over here. This is the unbalanced side. Ground's over here. It's going to come out over here balanced. So what I'm putting in here is just a sine wave, and what I'm going to get out here is a sine wave and another one with equal and absolute and opposite balance. Okay, thank you for putting up with my physics lecture. I know you all enjoyed it desperately, but let me get back on screen for a second. And, oh, I guess I can't get on. I don't know what I'm doing. Oh, I know what I'm doing. There we go. Okay, so again, what we're doing is we've got a 3D printed frame for this that will hold an inverted delta antenna. I've got all the 3D prints that I'm going to share with you guys, and what we're going to do is build a balun that'll go on that. So the balun itself is 3 prints. I threaded this, although it turns out that ended up being a huge waste of time because it leaked anyway when I went to pot it, but I tried. You could just not have the threads and it would be just fine. But the idea is that we wrap the coils and we set them in here. We put this in, wire everything up, close it, and we're done. And I have a little over an hour before I have to leave. So we're going to get this done. This will be a good time. All right, we're using some 240 43 cores. And I might have to grab, no, the other one's in the clamp. Okay, I think that'll be fine. Where did I put the clamp? Here we go. So we've got 2 of these. We have some wire. This happens to be 18, but I think 16 is recommended. But this is just enamel magnet wire that I have twisted together and wrapped the ends on. Woo! We've got some BNC connectors. Although we just need 1 of them. I've got 2 here in case I screw something up. And then we've got some, oh, I am a messy boy. I'll just grab another one. But then we've also got the banana posts, but I'll just grab a couple more of those out of storage so we look for them. All right, so how long do these things need to be? That is a fantastic question that I'm afraid I don't have a terribly good answer for you on. There is a diminishing returns after you wrap these. The number of wraps doesn't really affect the impedance. The impedance is more affected by the wiring. These things appear to be about 28 inches long if you're making your own. And at some point, you're going to have to strip the wire off the ends of these. I don't know that I have the exact right length yet. It's probably going to have to be more. But the easiest way to do that is usually with sandpaper or something. They do make these really cool tools. They're about 40 bucks. And they just go on and they spin, spin, spin. Do that a little bit. Woo! And that is about the easiest way to do it in my opinion, but there's lots of different ways that you can do it. So, yep, we're doing a 4-to-1. I'm sorry, Andy. We are doing a 4-to-1 guanella. Okay. Now, on the cores, we're going to have these things wrapped in opposite angles around them, and the way that I'm going to keep track of everything is I'm going to have the blue sides facing each other. One is going to go this way, and I'm going to hold these up to show you in just a second. One is going to go this way. So I'm just marking these so I can keep track of what's what, because I don't want to screw that up later. All right, let's get an overhead view that everybody can see. I don't think we need me anymore. There we go. Although I would imagine you guys would appreciate it if I made it a little less blurry. Come on. Okay, that's probably as good as we're going to get on this setup. So the way that I am going to start this is by... Oh, I'm not winning the green screen. I have no idea what I'm doing with this green screen anymore. Okay, I'm just going to be green. So I'm going to start with the middle here. And I'm just going to feed this up so it's grabbed on the bottom of that. Then, as much as I can with this clamp that I'm trying to not crush the core with, but can be a little tighter. On this first one, I am going to wrap in this direction. So the one closest to me goes to the right. The one furthest from me inside the core is going to go to the left. And for me, I am just going to start here in the middle, drag them through. Don't like that knot that's showing up. And I want these things to be as close to the ferrite as I possibly can get them. And I have heard tale of people using hammers to make this happen. I've heard tale of people using pliers to make this happen. Totally up to you. Just try not to damage the enamel. All right, I'm going to get rid of that clamp. It's not really doing me any more good. We're just going to go to the overhead view, and you can watch me there. Okay, get rid of that knot. I twisted these things up by holding them both in a set of clamps at one end and twisted them about 20 times each. I'm sure there's an optimal number, but I do not know what that number is. And just to make things a little tighter, I'm going to grab these things and yank on them. All right, so while I'm making that, let's see if there's any chatting that we can do. How'd I do on the explanations of the lens icing model, Andy? Did you catch that, or was it a little too crazy? I can always cut that out of the final. All right. Don't want these things to necessarily overlap, and we'll work on the spacing a little bit more in just a minute. Looks like I can do one more wrap through here. Good. Okay. Well, I'm glad to hear it. I'm just going to use this for QRP, but if you are doing higher power, you can get some pretty high voltages in these, and the solution to that is to wrap these things in heat shrink or PTFE. Okay, so there's winding number one. Winding number two is going to happen the same way. I'm going to fold the wire in half. Start on the blue side, and in this case, the one closest to me is going to go to the left first, and the one behind me is going to go to the right. So in doing this, I'm getting the wires wrapped in a right-hand direction on one core and in a left-hand direction on the other. And again, you just kind of want it as tight as possible. So Andy, if you were here for the 3D files, I have not uploaded them yet, my friend, but I would be happy to. I've got an appointment in a little over an hour I'm going to have to hit, but I could always do it later tonight. Okay, so there's half the windings. Now I'm just going to continue around. This one's looking a little better than the previous. The easiest way to figure out how much wire you need is to wrap it with a string first. And then once you have the string, it'll tell you. Let's see how many more we can do here. Looks like I can get one more. All right, now we've got 2 cores. Let's get back to the overhead view for you. And make it a little unblurry, less blurry. There we go. Manual lenses. All right, so here's our 2 cores. I can do a little bit of a better job on working on the spacing on these things, but that is pretty much the winding. So I took these 18 inches of wire, stripped the ends, gave them about 20 turns so that they're doing this sort of number. And now I'm going to put one on the other. And let's see if I can pull these tighter. I'm going to start doing some electrical connections. I used 2 different colors of enamel just because it'll be easier for you guys to see what nonsense that I'm involved in. And also on the 3D print, this would be a good time to show you this next part. The 3D print has, they're kind of hard to see, but there's these 3 reference markers, 1, 2, 3, that match up with 3 reference markers here. Right here. 1, 2, 3. So you can, when this thing is threaded on, this is the side of the container that is going to be lined up with those 3 spots. I also put a 3D printed a spacer just to keep the coils from rubbing on each other long term. So this guy, and this guy. All right, let me go back to my diagram real quick. This is my, oh, we got to go overhead wide. So this is my Guanella Balun. I've got red and orange wires feeding into each one and red and orange wires coming out of each one. What I'm going to want to do over on this side is connect the, yeah, I guess it wouldn't matter, but I'm going to connect the 2 oranges together, short them out. I'm going to give the 2 red, and those are going to get connected to the Balun side. I'm going to have red, red, orange, orange on the left side. I think I built the other one in the exact opposite, but I think that's just simply the way that I labeled these. Will that matter, Andy? Tell you what we're going to do. We're going to create it just like the other one because I made the other one and I tested it. We're going to make it this way. So I'm going to short the 2 oranges together, and then I'm going to have a red balance, but then I'm going to have orange red mixed, orange red mixed. So that's what we're doing. Because I built that, I tested it on my scope, I know that works. I don't want to have any issues with the currents inside and outside the coil and all that stuff. So anyhow, I might have to do a little bit of cajoling, but these coils fit, not well, but they fit, and they go inside. All right, we'll start heating up the iron and go from there. So, diagram, 2 oranges. That's what I'm looking for first. So I'm going to get those things isolated by untwisting them. And then I'm going to get them married together. And I'm going to get some pliers to hold them while I solder. And Andy says this will be fine for 50 watts. I'm going to trust him. Thanks, Andy. And all you others out there in TV land watching this unannounced stream, please do say hi. Let me know who you are. Like, I'm not going to chase you down or anything, but it's always nice to meet new friends. Okay. Let's let you guys get up close and personal on cam 3. They need to make this thing so that I could have somebody else controlling the switcher, but I don't know how you would do that. I'm always a big fan of flux. To deoxidize and lower the surface tension. And then, come on, Mr. Solder. There we go. Gonna heat that up. Solder goes where flux flows, so come on, big guy. Let's add a little heat here. Make sure we're melting. Make sure the tip's tinned. I don't know if you guys can see that at all, can you? It's very small amounts of solder so far. I only have a small one available to me. I am going to show you a trick that I sometimes do in cases like this when my depth perception gets the better of me. Whoops. I'm just going to wrap some solder around it. Let's do it this way. I've already fluxed it, so now I'm just going to heat this up. And we'll let it flow right in between. You can see that there is probably some enamel that wasn't cleared off there. That's keeping those things from sticking. So now those two center orange ones are stuck together. That's what we want. We can trim off the end and fold those over, and a little bit later we can cover them in heat shrink tubing to prevent any short circuits later on. Alright, those two are done. Let's go back to the diagram and figure out what we're going to do next. So this is done. Next up, I need red and orange paired to the center point of the the BNC connector, I'm going to need red and orange to the ground of the BNC connector. On the other end, I'm going to need red and red to the outputs for that. So these are my two red to red for the output of the device. That's going to go to the banana, and then I'm going to have red and orange and red and orange there. So I don't have a ton to work with here, but I've got enough, and I'm going to make up the difference in with heat shrink tubing. So the first thing I'm doing is isolating and separating those, which I can give you a better view of. I didn't really quite have enough wire. I could have used a little bit more, but what's done is done. So what we're going to do is marry these two together and then marry these two together. And you'll see that there could be some short circuits, so I'm going to fix that with heat shrink tubing to prevent it. Oh, what have I done? I tell you, I'm the reason I can't have nice things. Okay, we're going to make this work. So I'm going to take a little bit off this guy. And a little bit more off this guy. And then I'm going to find some heat shrink. Got a ton of it here. See if I have any that's thinner. I do not. Andy, I've got another question for you. How's my audio doing today? I've been having a lot of trouble with this mic setup. Let me know in the comments below. All right. I'm just going to protect these things a little bit. So all I'm trying to do now is get this heat shrink down over the exposed wire. I might stop and look for some, I think I want some thinner heat shrink so I can push it down a little bit further. So if you guys will indulge me for a moment, I'm going to do that. If I was heat shrink, where would I be? Here we go. So maybe about that long. Again, since I pre-stripped this stuff, I could potentially have caused myself a little bit of trouble, and I could have made these wires a little longer too, but I'm just pushing it down over these things just to make sure there are no unknown shorts. Right? I don't want to know every bit of trouble that I'm causing. And I might need to add a little bit of wire to these two, but again, not the hugest deal in the world. The enamel is still plenty long on these, so it's not really an issue there. I just have to mechanically connect them and then I will electrically connect them. Solder is not a very good mechanical bond, so whenever you can, make mechanical bonds for strength. Don't worry, we're going to cover these too. Again, I always like to use a little bit of flux. Solder goes where flux flows. It lowers the surface tension, deoxidizes any metals. And you guys are probably yelling at the screen right now. Like, why are you all over the place with that solder? And the truth is, I've got pretty horrible eyesight. Most of this stuff, if I wasn't on screen, I would be doing under a microscope. And it wasn't that way when I was younger, I'll tell you that much. But that's okay. All right, so there's one. We'll cover that. This one's going to be a little bit trickier in that they're both short. So I'm just going to pick one, and then we'll likely just add a short piece of metal just to make life easy. So I grabbed another piece of enamel wire. I'm going to make a lengthener. And all I'm doing right now is just drawing it through the tool. Tell you, if I had gone for 19 inches instead of 18 and a 18, I wouldn't have had this issue, but I was getting stingy with the wire, getting too clever. So now all I want to do is get these things bonded together. And then once we solder them, I'll put on some heat shrink and all our issues will be gone. Okay. Gonna do our flux thing. We're going to do our wrap it around trick. This is like 4 mil solder, so there's not much to it. Okay. Then we're going to dump a bunch of heat into it until it melts. And surface tension should have it travel in that whole cleaned area for us. Does it look great? It doesn't look great, but it'll do just fine. That'll do, little donkey. That'll do. We don't need that part anymore. And then I am probably in a good spot to shrink those and cover them. And shrink cover this one. do I have 2 viewers on an unannounced stream with a channel my small? YouTube always amazes me. Okay, so this is our connector. We've got 2 for the bananas, which I'll grab another one in just a second. I've got ground and center, and it doesn't really matter which one's which. And this thing is now ready to install in the case. "59 same time slit crackle." Is that a football play, Andy? What is that? 59 same time slit crackle. I don't know what that means, my friend. Okay, let's get this. Yeah, the thread, again, was really overkill. I don't think I would do that again on this design. It would have been fine to just have a slip joint. I did this because when I did the epoxy pour, I assumed the threads would keep the would keep the epoxy in. They did not, rather disappointingly. And now this thing isn't rotating around the last little bit. Oh boy, you guys are silly, aren't you? Come on. Okay, there's that. And that. There's that. And that. Oh, 59th the same. I find all the stream. Yes. Yes, you do, sir. Yes, you do. Okay, we're ready for that. Let me grab a bean or a banana, and we'll be good. There ain't one of these. There. There's one. Amateur radio caps by A14NW. Hello, A14NW. How are you today? Thank you for joining us. We are building a Balun for an inverted delta antenna. These exist on the market. The thing that makes this one special is that it is coaxially arranged so that it will go on the same post that the antenna does, so you can mount it. That's what makes this thing kind of cool. And I've done the wrapping. All I'm doing now is the soldering and the final assembly. And there are dogs barking in the other room. My apologies on that. Okay. They always give us so many nuts and bolts for these things. Whoops. Missed by that much. So, Amateur Caps, how you doing today, sir? If we've never crossed paths, nice to meet you. I have a couple of these kind of terminals to make my life slightly easier or slightly more difficult, depending on your perspective. I'm going to get them centered before I heat them up, and then I don't have to worry about getting the length wrong, and we'll come back and put on the rest of the hardware in just a second. I just need them to be approximately correct right now. So Amateur Caps, you still haven't told us who you are, buddy. I'm Mark. You obviously know Andy, but then again, who doesn't? Get that wire out of the way, maybe that'll fix it. Or maybe it's a secret. Maybe we can't know your identity because you're a spy. Is that it? Amateur Radio Caps, are you a spy? Because, you know, if you're a spy, you have to tell us. Those are the rules. Come on. Okay. Get that in there. Get that in there. Get that wire. I might have to cut that after, once it's back out. Okay. What I've been working on is this. I probably should have shared that with you earlier. I'm going to solder those things in, but first I wanted them in the right location. You can never use too much flux, although you should clean it off afterwards, even if it's no clean. The difference between no clean and regular flux is no clean remains acidic, and it can slowly dissolve your joints, which is never a good thing. But you should always clean your boards afterwards anyways, because you never know what contaminants are on them from the manufacturing process or assembly process or the Cheeto eating process. Funny thing in assembly houses, the contamination rates go up after breaks and after lunch. Okay, so those two are on and done. I'm going to take these off and put on the rest of the hardware now, just so I don't forget later that I didn't. The way that I tend to clean boards is I will put them in a ESD bag, and I'll put some isopropyl alcohol in there, the strong stuff, and then I will take that bag full of isopropyl and I will put it in a water bath, ultrasonic cleaning water bath. The reason you don't want to fill the entire water bath is, I don't like the looks of that joint. The reason you don't want to fill that entire water bath is with isopropyl is it is flammable at the concentrations I tend to use it at. And you do not want to cause a fire. Let's see if we can heat that up a little bit more. Watch that flow. There we go. Okay. Next up, we've got to put that B and C in. There's a couple different ways that you can do this. The way that I did it in this other one, and I don't know that I have the right part handy, so I might hold off on it, but I don't know if we're going to be able to see it. I've got a little tab there. So we've got the center conductor done, And then I don't know if you can see it, but it's a little baby solder tab that I soldered to and then screwed to. That's how it's connected. But that's not the only way that I could potentially do it. It's just a way I could potentially do it. I do know that I'm going to have to, or at least want to, cover this. So I'm going to put on a little bit more heat shrink. And we'll get that stuff wrapped down. And cleaned up. You're also supposed to use heat guns for this, not butane torches, but don't tell. Don't tell OSHA. Okay, so the first one that I'm going to terminate is this guy. Sorry to block your view there. So this guy is going to sit right there. I'm going to add a little bit of flux. To poke it back in, it seems. And find the end of the solder again. Boy, this stuff likes getting tangled. Okay, we'll let that cool and give it a second. Now all that's left is that last one, but I think I'm going to wait until I get another tab handy to do that. Okay, let's go back on screen for a second. Oh, come on, there we go. So anyhow, so that's pretty much it. I do have one last solder joint to make, but at that point you would take this, fill it with epoxy if you wanted to pot it, and there's some holes that, I mean, I would just glue the top on. You're never going to need to take this off anyway. And then there's some holes you can squeeze stuff through, but then that'll be it. That'll be your Balun. Now, I say all of that, and then I'm going to set this one aside because there's still one last bit of physics that I want to talk about. Remember that we said it needed to be balanced. Well, I need to prove to you that it is. And my oscilloscope needs to turn on for that. Come on, little guy. Oh, don't do that to me. Don't do that to me. Is it going to spin up? You know, we're going to do the whole have you tried turning it off and on again thing. There it goes. Okay. So we're going to give that a second to spin up, and then while we do that, I'm going to tell you what, I'm going to put a couple tools away and tell you what I'm going to do. And what I'm going to do is check for balance. I do not need tools for that, but I do need a couple resistors. the antenna that we're making has a characteristic impedance of, if I remember correctly, about 130 ohms. Don't quote me on that because I'm doing that from memory. And the output of your radio has about 50 ohms. So what happens whenever you have an impedance change is the energy hits that interface and then it gets reflected back, and you never want that. So we typically make tuners that will try to match the impedances by storing the energy reactively. All right, what I'm making right now is a resistor divider out of two 100 ohm resistors. So these resistors are going to be center tapped and tied together electrically at what we're going to call a ground point. And let's see if we can show this to you. Ooh. I don't think I need to be on screen for this. There we go. So I've just got a couple of resistors that are tied into this banana plug. Each one of these is 100 ohms, and they're pretty decent resistors. I have them wrapped around this center pin, and we're going to attach an oscilloscope ground here, a probe here on the left, and a probe here on the right. And what we're going to look for is, do we indeed have a balanced Balun? So this is the one that's already potted. And then I need my scope probes, which I have cleverly hidden. Or did I put them away? Or did I hang them? Looks like I put them away. All right. Are we still on screen? So this is probe 1. This is probe 2. That's our experimental setup. And what we're going to look for in just a second, I'm going to put the oscilloscope screen on, but what we're going to look for is, do we get a balanced signal at our frequencies of interest? For that, I do need a signal generator. I'm going to set up my SDR kits VNA to do that for me. So I'm just turning that on now. I need a 50 ohm feed line to go from the VNA output to the Balun input. So the VNA's providing single-ended, come on, don't fall off the back there. Okay. The VNA is providing single-ended output. The Balun's doing its thing, and what we're going to be looking for is, do we indeed get balanced output here? So I'm going to start off with, say, 5 on. All right, so now I have to find a way to show you my oscilloscope screen, which well, that's going to be interesting. Oh, I have an idea. I know how we're going to do it. Sean Technician. Hi, Sean. Oh, and I just minimized that. I didn't want to do that. Okay, here's what I'm going to do. I am going to show you my computer screen, and I'm going to put my computer screen on camera. Otherwise, I have to point a... Okay, so how do I show you computer screen 5? Input 5. Don't worry, this is all coming out in the edit wash. All right, we're going to have to clean this stuff up for you. And this is not an oscilloscope I use often, but let's do an average of okay. Then channel 2, normal average 64. Is that the same acquisition stream? Okay, let me double check my setups because, oh, one's DC, one's AC. That's not good. We want identical couplings. I want to make sure nothing's inverted. So this is interesting. Something's up because this worked yesterday. Okay, do I have a short in my setup? Or a bad connection in my setup? Because if something isn't properly connected, that would give me what I'm seeing. Let's try this again. So the issue that I'm seeing now, for you people out in TV land, is those are not indeed equal and opposite as I would hope. Which is weird because when I tested this Balun a day or two ago, they were. But I also don't remember the scope probes being this messy. 10 millivolts per division, 5 millivolts per division. So I'm not seeing equal amplitudes, and I'm not seeing... So let's take this apart. Okay, so with nothing plugged in, what are we seeing? So right now, all I'm doing is backing up, and I'm going to rebuild my setup and see what it is we're seeing. So right now, there's no inputs on the... This is what happens when you do things live. There are no inputs on the oscilloscope probes. So what I would expect to see on the oscilloscope is nothing, and that's pretty much what I see. Okay. Next up, let's add back in this isn't right. This is not what I would expect to see, nor is it what I saw. Uh-oh. Things have gotten worse. This is pointing towards an issue with the VNA. Maybe I need to pull out an actual frequency scope of some sort. Okay, so this is not plugged in on the other end. This is without the VNA involvement at all. And what we're seeing is some coupling to something, but there's no direct electrical connection. So let's plug back into the VNA and let's turn it off and on again. On. Okay. This is really weird. I don't have an explanation for this. We could go AC coupling. If any of you people out there in TV land do, I am happy to entertain it. The only reasons that I can think of, anything turned on today for the stream? Oh God, yeah, there's a lot turned on today that wasn't on the stream yesterday, Sean. There was a ton. I've got all sorts of video production crap and lighting that I didn't have before, so that could certainly be it. AC coupling, channel 2. See, because what I would expect to see is this, what I'm about to show you, but I cheated to get here. And the other thing that's missing too is it shouldn't be jumping around this much. And the amplitudes really should be equal and opposite. And I'm just not seeing that. So maybe we've made an antenna. Maybe we've got a loose connection. I mean, it could be, there's a lot of maybes that could be maybeing right now. Let's try it. Is it just that? That can't be. No, something's up. And I don't know what it is, but no earth on B and C. Oh, great suggestion, but this is a different one. This is the one that I potted. That would absolutely be correct, but this is the one I potted yesterday. I set the one that I haven't finished to the side. Otherwise, that would be an absolutely phenomenal suggestion, because that's kind of what I'm seeing here. To me, it feels like something's floating, like there's not a solid connection on something, but I don't know exactly what, because this isn't right. Since it's a screen capture, turn off the LED lights. Okay. Ooh. Sean, you're assuming a level of sophistication I do not currently possess. I cleverly tied the light switch into my monitor, my computer. It's all on one power strip. I don't know which one to unplug. Oh. Let's see. Okay, it's LEDs. I am absolutely adjusting this with my LEDs. Turning the knob, unturning the knob. Yeah, okay. So, I don't know how to deal with that other than to record it separately. But you're absolutely right, Sean Technician. We are influencing that, which makes me wonder, yeah, okay. I'll fix it in post. I've actually got some cool screen captures that I can show you guys in post. So anyhow, unannounced stream. Am I still transmitting even, or did I break it? I guess I am. I don't know. But anyways, interesting stream. Thank you for joining me. It was unannounced. I'm going to have this cut down into a much shorter, more palatable video, maybe with some better graphics. We'll see. And then I'll finish up the tail end with what these scope things are supposed to look like. Sometimes the light's power cable can be disconnected from the light itself. I wish I could show you the mess of just squirrel nesting cable that I have here. I, honest to God, wouldn't know which one to touch right now. I'd have to look. It's not good over here, Sean. I've got issues, lots of issues, but that's okay. In the next video, I'm going to do the much more simple build, which is this part, which holds these things for the antennas, so you can have your inverted V, and then we will get out and make some contacts. But I'm squeezing this in amongst my other responsibilities, and one of my responsibilities means I have to go now. So thank you all for joining me. If you don't know about Boondock Echo, look us up. It's a whole lot of fun. We'll see you in the next stream. Bye.